Welcome to the deep dive. Sometimes the biggest stories in science, they aren't the ones making all the noise, like space launches or big medical news.
Right.
Sometimes they're happening, well, kind of quietly, in the world of abstract mathematics.
Which sounds intimidating, maybe?
It can. But abstract doesn't mean it's not hugely important, and we're talking about something really monumental today.
Absolutely. The recent proof of the geometric Langlands conjecture.
Exactly. And this isn't just, one isolated thing. It's a massive piece of a much bigger puzzle.
The Langlands Program, people sometimes call it the grand unified theory of mathematics.
Quite a title.
It is. And our mission today, really, is to give you a shortcut to understanding what this huge proof actually means.
Okay.
We want to unpack it, look at who was involved in this, truly gargantuan effort,
Yeah.
and explore why it's not really an ending, but more like opening up, a dozen new doors for mathematicians.
So it's a launch pad, not just a conclusion.
Precisely. It's a deep dive into a real breakthrough.
It really is. So this proof for the geometric Langlands conjecture, it was just recently unveiled.
Right. The culmination of, over 50 years of work?
50 years, imagine. Like working on one incredibly complex puzzle for your entire career almost, and then finally seeing it click.
The scale is just staggering. It took a whole team, 9 mathematicians, led by Dennis Gatescory and Sam Raskin. And their work, it resulted in 5 papers.
Okay.
Almost 1,000 pages total.
1,000 pages. Just think about the sheer brain power, the persistence needed for that.
No kidding. And they're getting recognition, too. Gatescory got the Breakthrough Prize, which is what, US $3 million?
Wow, yeah.
And Raskin got a New Horizons Prize for promising younger researchers.
That's great to see. David Bensby, he's a top mathematician. He put it really well.
What did he say?
He said, it's a huge triumph, but rather than closing a door, this proof throws open a dozen others.
Ah.
And what he means is the big immediate win here is how it builds bridges. Bridges between parts of math that seemed totally separate before.
Right, like different worlds colliding.
Exactly. Imagine you're, say, a carpenter stuck on a problem, and suddenly you find out a plumber's wrench is the perfect tool.
Huh. An unexpected connection.
That's the kind of thing this proof allows. It lets mathematicians use tools from one area to crack problems in another, problems they've been stuck on for ages.
It's all about finding those hidden connections, those secret paths between different mathematical realms.
And that idea, that connection, it's really the heart of the whole Langlands program, isn't it?
It absolutely is.
Okay, so let's unpack this a bit. This grand vision, where did it start?
It goes back about 60 years. A young Canadian mathematician, Robert Langlands.
Just starting out.
Yeah. And he outlined this incredibly ambitious idea in a handwritten letter.
Handwritten to who?
To the famous Andre Weil. And Langland's goal was, it was audacious.
Okay.
He wanted to connect 2 really major but very separate branches of math.
Which were?
On one hand, number theory, the study of whole numbers, integers.
Stuff we learn in school, basically.
At its core, yes. And on the other hand, harmonic analysis.
Harmonic analysis. That sounds more complex.
It's about how you break down complicated signals or functions into simpler waves. Think sound waves, maybe.
Okay, I think I follow. So numbers and waves, they seem pretty
They
different.
really do. And Langlands was looking for deep, unexpected connections between them.
And just to give people a concrete idea of how powerful this is, Fermat's last theorem,
Yes, the famous one.
Andrew Wiles' proof back in 1995, that huge deal.
Took centuries to solve.
Right. And that proof, it was actually a specific example, a kind of test case for the Langlands program.
Exactly. It showed the power of these connections Langlands proposed. It really highlighted the unifying potential.
So it's not just abstract theory, it solves real old problems.
Definitely. Which is why Edward Frankel, he's a mathematician at Berkeley,
Wow.
he calls the Langlands program the grand unified theory of mathematics.
Like in physics, unifying forces.
Very similar idea, an overarching framework trying to connect everything.
Okay, so that's the big picture, the Langlands program. Now let's zoom in on the geometric side. That's what this new proof is about.
Right. The geometric Langlands conjecture, developed first in the 1980s by Vladimir Drinfeld.
And how is this different from the original Langlands idea?
Well, the key thing is, while the original Langlands connect mathematical worlds that seem really far apart.
Like numbers and waves.
Exactly. The 2 sides of the geometric conjecture, they're actually much more closely related from the get-go.
Okay, how so?
Both sides deal with properties of something called Riemann surfaces.
Riemann surfaces. What are those, roughly?
Think of them as 2D surfaces, but they use complex numbers for coordinates. Shape-wise, they can be like spheres or donuts.
Like a torus.
Yep, or even like pretzels with multiple holes. Complex, curvy shapes.
Got it. So the geometric conjecture links two different aspects of these donut or pretzel shapes.
Essentially, yes. One side is about the shape itself specifically, all the different ways you can draw loops on the surface.
Loops, like tracing paths?
Kind of. Imagine a donut. You could loop a string around the outside, horizontally,
Okay.
or you could loop it vertically through the hole and back around. Those are distinct loops. This side describes all those possibilities, mathematically, using matrices.
Right. And the other side?
The other side deals with something called sheaves, which are tools from algebraic geometry.
Sheaves. Okay, that sounds technical.
It is a bit, but think of it like assigning some kind of mathematical object, like a vector space, where you can add arrows and stuff to different points on the surface.
Like assigning a temperature value to points on a map.
That's a decent analogy. Or
Yeah.
like a gravitational field assigns a strength value to points in space. Here, you're assigning more complex algebraic structures.
So the conjecture says the way you can loop strings is deeply connected to the kind of algebraic info you can attach to points?
That's the core idea.
Yeah.
A hidden link between the geometry, the loops, and this algebraic data, the sheaves.
And you said these two sides, loops and sheaves, are sort of closer than the numbers and waves in the original Langlands?
Yes, conceptually, they feel more related to geometers, and that's really significant.
Why is that?
Because many mathematicians suspect that understanding this geometric version, where the connection is maybe clearer, might give them crucial insights into the original arithmetic Langlands program, which is still much more mysterious.
Like a practice run on something slightly easier.
Maybe not easier, but perhaps more intuitive geometrically. Edward Frankel put it nicely again.
What did he say this time?
He said, to truly understand the Langlands correspondence, we have to realize that the two worlds in it are not that different. Rather, they're two facets of one and the same world.
So they're two views of the same underlying thing.
Exactly. And he thinks with these Riemann surfaces, the geometric setting, these two worlds sort of coalesce, giving us a peek at the unity behind the whole program.
This has been such a long journey building these mathematical bridges.
Decades of work.
The foundations go way back, right?
Yeah.
To the 90s. Drinfeld and Alexander Beilenson.
That's right. They did crucial early work exploring how to translate between these geometric loop properties and the sheaf information.
And they wrote a huge paper on it.
Nearly 400 pages. And incredibly, it was never formally published.
Never published. Wow. But people knew about it.
Oh, yes, it circulated. Then in 2012, Dennis Gatesgory, working with Dima Arrington, made the relationship much more precise. That was key groundwork.
Okay.
And after that, Gatesgory basically developed a step-by-step plan, an outline, for how the geometric Langlands proof might actually be constructed.
It's interesting, too, how the view of this proof has changed over time. Bensby said people are more excited now than they might have been 10 years ago.
Yeah, that's a great point. Why does he think that is?
He says it's because we understand better why it's the right kind of question to ask and why it might be useful for things in number theory.
Ah, so the community's appreciation has deepened. They see the broader implications more clearly now.
Exactly. It's like the groundwork laid over the years has prepared everyone to really grasp its significance.
That makes sense. And one immediate impact of the proof is how it's boosting research into local versions of Langlands.
Local versus global. What's the difference there?
Think of global as looking at the whole Riemann surface, the entire landscape.
The whole donut.
Right. Local lets you zoom in on tiny patches, like a little disk around one specific point.
Okay, microscope view.
Exactly. Understanding the behavior in these tiny local regions can tell you crucial things about the global picture. This proof helps connect those local details.
Now, here's where things get really fascinating, I think. Peter Schultz.
Fields medalist, yeah. A huge name.
You'd assume he'd just get geometric Langlands, right?
You would think so.
But he admitted it seemed incomprehensible to him for a long time.
Really? That's surprising.
Until Laurent Fargues proposed this geometric way of looking at the local arithmetic Langlands conjecture.
Ah, connecting geometry back to the number theory side, but locally.
Exactly. And Schultz and Fargues, they worked together for 7 years on this.
7 years. Wow. And they built what Schultz calls a wormhole.
A wormhole between
Between the global geometric world, the stuff Gatesgory's team proved, and the local arithmetic world, the number theory side.
So like a shortcut connecting these different mathematical universes.
That's the idea. It allowed them to literally transport methods, structures, insights from the geometric side over to the arithmetic side.
And did it work?
Yes. It helped them prove a version of the local arithmetic Langlands conjecture related to p-adic numbers, which are crucial in number theory.
That's amazing, building an actual mathematical wormhole.
But the connections don't stop at just bridging different parts of math.
Right, there's the physics link, too, which is just mind-blowing.
It really is. It involves something called S-duality.
S-duality, from quantum field theory.
Exactly. Physicists started exploring this back in the 70s. It's a deep symmetry.
Okay, what kind of symmetry?
Basically, in some physical theories, if you swap the roles of electric fields and magnetic fields in the equations.
Like in Maxwell's equations.
Precisely. If you swap them, the equations describing the physics actually stay the same.
Ah, so there's this hidden balance.
Very profound one.
And then, Witten and Kapustin connected this to Langlands.
In 2007, yes, Edward Witten, the physicist, and Anton Kapustin, they made an incredible discovery.
What was it?
They showed that this S-duality symmetry, when it appears in certain four-dimensional quantum theories.
Like the ones describing particle physics.
Yes, including the Standard Model.
Oh.
That symmetry turns out to be mathematically the same as the symmetry underlying the geometric Langlands correspondence.
Wait, the exact same mathematical structure?
The very same. As they put it, these seemingly esoteric notions of the geometric Langlands program arise naturally from the physics.
That's just staggering. Math mirroring fundamental physics or vice versa.
It's profound. Witten suggested geometric Langlands could be seen as a shadow of a deep symmetry in quantum physics.
A shadow of physics in pure math.
Which has inspired people like Min-Young Kim to use physics ideas as metaphors, as tools to think about hard number theory problems.
And now others are taking this even further. Benz V again.
Yes, Benz V, along with Yanis Sekularitis and Akshay Venkatesh. They have this ambitious project.
What are they trying to do?
They're trying to reimagine the entire Langlands program, both geometric and arithmetic, using the language and ideas of quantum field theory.
Wow, so using physics as the framework for the whole thing.
Kind of. They're translating physical concepts, like dual descriptions of materials, into a huge web of connected mathematical conjectures within Langlands.
That sounds incredibly complex.
It is, but they're getting striking results. For instance, they found a two-way relationship connecting parts of harmonic analysis and number theory.
The original two Langlands worlds.
Right. And this relationship, seen through their physics lens, actually mirrors the structure of the geometric program as well.
So it's all starting to look interconnected from this new perspective.
It suggests an even deeper unity, potentially linking math and physics at this fundamental level.
So where does all this leave us? What happens next? The proof is out there.
Well, first, the formal peer review needs to happen. Almost 1,000 pages, remember?
Right. That's going to take years, probably.
Years. But the confidence in the result is very high within the community.
And Gatesgory isn't stopping.
Not at all.
Yeah.
He and his team are already working on extending the proof.
Extending it how?
The current proof handles the unramified case. Think of it as the well-behaved, smooth parts of the Riemann surface.
Okay.
Now they want to tackle the ramified case. This involves points where things get more complicated, more singular, like punctures on the surface. It's technically much harder.
More complexity to wrestle with.
Exactly. And Jessica Finson is one of the key collaborators on this next stage.
What's her role?
She studies related mathematical structures, representations of parietic groups, which are crucial for incorporating this complex local information near the punctures into the overall global picture.
So, adding the tricky bits into the framework.
Precisely. As Vincent herself said, somehow the proof's the beginning and not the end.
That really sums it up, doesn't it?
It does. What started as these, deep abstract ideas connecting different bits of math has blossomed into this huge collaborative effort that spans number theory, geometry, algebra, and now even quantum physics.
It's become a real crossroads.
A testament to where pure mathematical exploration can lead, and the power of mathematicians working together on these immense problems.
So maybe the Langlands correspondence isn't quite the absolute grand unified theory of mathematics yet?
Perhaps not definitively proven as the one theory.
But this proof, the geometric part, it's undeniably become this incredible nexus of ideas.
Absolutely. It's going to influence so much research going forward.
In math, and maybe even in physics.
And it leaves you wondering, like Edward Frankel said.
What was his final thought?
He said, "The Langlands correspondence points to much deeper structures in mathematics that we're only scratching the surface of. We don't really understand what they are. They're still behind the curtains.
Still behind the curtains, it really makes you think, doesn't it? What other secrets, what deeper connections will this breakthrough help us uncover in the future?
It's an exciting time to watch.